So let's look at electric current in a little more detail now. Now, current is the rate at which charged particles cross a section of a conductor in a given direction. So we can write it down as an equation: I is equal to Q over delta T for a constant current, or if we have a current which is varying with time, we can write, well, I is equal to dQ dt. In these equations, Q and dQ are the amount of charge crossing the given section of the conductor, and this is in the time interval delta t or dt. Now, current is measured in amps, which has the symbol capital A. This unit's named after the French mathematician and physicist André-Marie Ampère, who was conducting electromagnetic experiments at around the same time as Ørsted and Biot and Savart. So current is literally comprised of electrons moving through a conductor. Usually we talk about conventional current, which actually has the opposite direction to the direction the electrons are moving. So when we think about conventional current, sometimes we think about it as the flow of positive charge, even though current is literally comprised of negative charges moving in the opposite direction. Now, I want you to imagine a conductor such as the one shown here with cross-sectional area A and length L. While there's no electric field, the electrons inside that conductor, many of them are free to move, and they are moving about randomly fairly fast. If we now apply an electric field, they continue to move about randomly, but imposed on that, they've got a drift velocity. They all start to move in the same direction. And so we can describe the drift speed, which is their average speed. This is represented with the symbol Vd. Now, the drift speed is actually surprisingly small. So if you think about the wiring in your house, the drift speed of the electrons through the wires is around about 10 to the minus 4 to 10 to the minus 5 meters per second. Now, we can compare this with the random speed of the electrons in the conductor, which is around about 10 to the 6 meters per second. So while the drift speed is small, it is accountable for the electric current. Now, one thing we'll want to do is we'll want to know, well, what's the total charge on the charge carriers inside our conductor? So we'll let N stand for the number of charge carriers per unit volume. We can then see that the total charge on the charge carriers in this volume is going to be given by Q is equal to NALE. So in this equation, NAL tells us about the number of charge carriers inside our conductor, and E, that's the charge on the electron, so that's the charge on each of these charge carriers. So when we multiply those together, we get the total charge on our charge carriers. Now, considering the electrons moving through our conductor here, they're moving with a drift speed Vd, and so we can calculate the length of time it takes them to move through this conductor, and that's given by T is equal to L divided by Vd. So we can now use this to calculate the current inside our conductor, because we know that the current is equal to Q over T, and we've just shown that Q is equal to NALE, and that T, the time it takes them to move through that conductor, is given by L divided by Vd. So you can see in this equation the L's are going to cancel, and we end up with I is equal to NAVDE. Let's now consider placing this conductor with that current flowing through it into a magnetic field. Now, when we place it into a magnetic field, the moving charge carriers are going to feel a force because we've now got charges moving through a magnetic field. And we've seen that the force in this case is described by F is equal to QV cross B. So in this particular case, we have F is equal to Q, where Q is the total charge on the charge carriers, VD cross B. And we've got an expression for Q. Q is equal to NALE, so we can substitute that in, and then we've still got the VD cross B. Now, VD is in the direction that the charge carriers were moving. If we say that they're moving in the L direction, then we can remove the vector from VD and instead place it on L. So we've now got the equation F is equal to NAVDE L cross B, and this is nice because NAVDE is just I. So we've now got F is equal to I L cross B. So this is an equation that we can use to calculate the force on a certain length of current carrying wire when it's placed in a magnetic field. So again, this is a cross product, so we can use our right hand rule to work out the direction of that force. So in this rule, the fingers once again represent the magnetic field lines because there's lots of them. Our thumb now represents the direction of the conventional current, and the force is out the palm of our hand. So let's have a look at a demonstration now where we'll show that a current carrying wire does indeed feel a force inside a magnetic field. So here I've got a demonstration that I love, but before I do it, I want you to make a prediction about what happens. So what I've got here is a car battery, which is supplying a strong current. Here I've got a horseshoe magnet. Horseshoe magnets are nice because they create a constant magnetic field between the poles. So the North Pole is closest to the camera and the South Pole is behind, closer to the back wall. And here I've got a switch. I need the switch because I can't leave a large current flowing through a wire for very long without it overheating and possibly catching fire. So before I switch the switch, I want you to make a prediction about what's going to happen to the wire. So remember, current flows from the positive side of the battery, the red side, to the black side. So it is traveling this way. The current is moving to the left. So make a prediction about what is going to happen to the wire when I close the switch.